Hello, and welcome to General Astronomy Lecture 1, an introduction. Before we begin, I would just like to mention that I do make these videos publicly available on YouTube, but this course is tailored specifically to my General Astronomy course, and it might not cover everything that you, perhaps a visitor from YouTube, might be interested in. So I won't be able to cover everything, again, because it is tailored to my course. But that said, if you do have any questions at all regarding astronomy or anything I've said, or even if you have questions about things that go a little bit beyond what I've said, or you want more, I might be able to help you out or point you in the right direction. So, absolutely feel free to comment on any of my videos, and I'd love to hear from you. So, just let me know if you need anything. That said, let us begin. In this lecture, all we're really going to do is just cover a broad, range of material. We're just going to start out by looking at some pretty pictures and talking about what they're showing. And then much later on in the course, we will get into very specific detail on how everything works. So let's just jump right into it. So I think most people might be able to guess what this is an image of, I would hope at least, since you see it almost every day. So in my actual physical course, I would ask what this is a picture of. And it is hopefully quite obvious that this is just an image of the sun. But then, I would start to ask, well, what is the sun? And a common answer is that it's a ball of gas or plasma. For people that know a little bit more, they might say that it's something that has nuclear fusion and ideas like that. So yes, the sun is a star. It is technically a giant ball of gas and plasma, and it is defined as a star because it is converting hydrogen into helium in its core via a process known as nuclear fusion. Nuclear fusion is the requirement for any object to be considered a star. Also, there is a secondary requirement of hydrostatic equilibrium, which basically just means that the star isn't expanding or contracting at all because of a balance between the inward pull of gravity and an outward pressure given off by that nuclear fusion radiation. But we'll get into that a lot more later on. The basic idea is we are looking at the sun, and it is a star. Here's another image that is quite common to us, since this is a picture taken from Earth, looking up at the sky. This is an image of the moon. Very simple. The moon is a satellite of Earth, which means it's a body that orbits around the Earth. Note that the term moon and satellite are often used interchangeably. Technically, the moon is the name that we give our satellite. So a satellite is any object that moves around another planet. And we also see some stars here. Considering the lighting, though, and the lack of stars, this is probably in a suburban area or close to a city. Or the sun could just be setting recently, but you don't see many stars in this photo. Contrary to that, though, you see very many stars in this photo. Now, this is a photo that maybe people where I live right now are familiar with because it's dark in the regions where I live. But I grew up my entire life in a big city, in Milwaukee, Wisconsin. And for probably the first 20 years of my life, I would say, never saw anything like this image until I moved out into the country. So, if you don't know already, this is an image of a ton of stars, but there's a defining feature moving from the top left to the bottom middle. This bright band that you see is the Milky Way. Not the candy bar, although that wouldn't be too bad either. This is the Milky Way galaxy. It is our own galaxy, the galaxy that we live in. It's our host. It's where we live. What we're doing in this image is looking upward at the plane of the galaxy. So our galaxy is a big disk. But if you look at it from the side, it looks just kind of like a long, elongated object. And that's what we're seeing here. We're looking along the disk, or into our galaxy, where the galactic center is somewhere in the middle here. So it is a dense collection of stars. But if you're near the city or if it's too close to dawn or dusk, you won't be able to see this because it's a pretty faint object in the night sky unless you take a long exposure photograph, which this image certainly did. So not many people have actually seen this Milky Way in the night sky. They might have seen it in pictures like this, but not with their own eyes. And it's just tough because it's such a dim feature. In fact, there's a funny story about this. In 1994, I believe, Los Angeles experienced a powerful earthquake, something like a 6.4 magnitude earthquake, and it knocked out power to a majority of the city. And that is a huge change for people. It's one of the biggest cities in the country, so it's very bright. And so when the power went out, the Milky Way didn't suddenly appear, but it appeared to them for the first time potentially in many of these people's lives. And in fact, it was so surprising to people that the police in Los Angeles actually got phone calls, 911 calls, for some weird, mysterious object in the sky, when really all they were doing was looking at their own home, their galaxy, the Milky Way, in this image. So just kind of a funny story, that there's a big difference between what you can see in the night sky depending on where you live. But regardless, it's still a very fascinating thing. Okay, these are some more images that might be familiar to you, especially the image on the left. It's a very common photo. All three of these images, while different on their own, are similar in the fashion that they are all considered nebulae, or a nebula. But there are three types of nebula that we will get into a lot more detail on in lecture something like 21 when we talk about the births of stars. But we can run through them very quickly. On the left, this pink image, we have what's called the Horsehead Nebula. Because, as you can probably tell in the center here, this structure sort of resembles the head of a horse. This image is of what we call an emission nebula. Emission nebulas always have this pinkish hue or glow to them. These are nebulas that are near really hot and typically young stars. We consider them to be O and B type stars, which you'll learn about eventually. It's often so hot around these stars that gases become ionized. There's a lot of energy, and they're excited. And through a process of recombination, when you have things moving around and coming back together, they will give off this pink glow. And that's what you see in these emission nebula. So I'll actually tell you some of the specifics of that later on, but for now, that's what you need to know. And these are often regions where star formation has just occurred to give you those hot O and B type stars. In the central image, we have a reflection nebula with a characteristic blue color. So all emission nebulas are pink, all reflection nebulas are blue. It's in the name what is happening in these photos, or in this photo. These stars are shrouded in some gas and dust, and their light is being reflected off of that material. So they will always have a bluish color, and I won't go into it too much right now, but it's the same kind of reason why our sky is blue during the daytime. It has to do with how light is being scattered and what wavelength of light passes through in a certain way. So in the same sort of sense that our sky is blue, these reflection nebulas are also blue. The last image, even though it looks maybe less beautiful, is absolutely fascinating and very important for us even. We have on the right a dark nebula. Never would have guessed how it got that name. But these are nebulas that are very dense. So there's not just a void here. There's not like some crazy thing going on in space where suddenly stars are disappearing. It's just a very dense cloud that happens to be sitting between us, the observer, and the stars in the background. So there are just as many stars here in the middle as there are elsewhere, but there's something blocking it. Kind of like perhaps fog on a really foggy morning blocks like your landscape view behind that fog. Same kind of idea. These are regions of very dense dust and gas out in space. And this is important because you need something that dense to start forming stars. When these particles get close together, gravity can drive collapse and start to form stars. So these dark nebulas are very important in star formation. So wherever you see these dark regions, you can probably assume that stars will be forming or have been forming for some time. Okay, speaking of star formation, to me this is one of the most incredible photos that's ever been taken. At first glance, it might not look like much, but what we're looking at here is what we call a protoplanetary disk. It's a disk of material, and in this case it's still very hot material, probably all molten gas, or well, molten material, and hot gases. So what's happening here is this is the birth of a star system, kind of like our solar system, where you have the sun at the center and planets around it. What we see here is the early stages of something like our solar system. We have material coalescing at the very center, forming a star, so this is what we would consider a protostar, something that's heating up and getting really warm, but it hasn't gotten quite hot enough for fusion to occur and call it a star yet. But what's most amazing to me is these dark rings around the protostar. What's happening here is this material is starting to clump up into balls as it orbits the central protostar. So these little balls of material are orbiting and sweeping away the material as they orbit. So what we're actually seeing here is the formation of planets. This is the only photo that I think has ever been taken of something like this, at least in this much detail. You can actually see planets forming and sweeping out their paths. So perhaps in a few million years, when this thing develops further and further, it'll eventually most likely get hot enough for a star to form here, and potentially this could be a star system with multiple planets, depending on how the material comes together and accretes as time goes on. But an incredible photo. So this might be kind of what our own solar system looked like many years ago. Okay, so that's sort of the birth of stars. Well, what about the end lives of stars? So here I have 4 images for you. At first glance, again, they might all look about the same to you if you don't really know exactly what's happening. But I did divide these in a specific way. On the left, we have one type of thing happening, and on the right, we have another. On the left, we have what we call planetary nebula, or nebulae. They have nothing to actually do with planets. The reason they're called planetary nebula is because when they were first observed, we didn't know what they were. They looked like just little bright spots in the sky, so we, back in the day, called them planets. So what's happening here is there is a star at the center of each of these images, and when a star gets old, very old, not to the point where it's dead, but close to being dead, the stars will expand. Our own sun, for example, will expand to the size of Earth's orbit. In other words, the outer layer of our sun, billions of years from now, will be so large that the outer layer reaches about where the Earth is now. So hopefully we figured out a way to get off the planet by then. But if a star gets to be too big, if it expands too much when it's starting to die, gravity can't hold the outer layers of that star anymore. And as a result, it will be beyond that gravitational realm, and that material can fly off into space. So that's what you're seeing in these 2 images on the left. We see a star that has expanded too much, and essentially it has shed its outer layers out into space. So the glowing regions that you see are the outer layers of those stars being shed off into space. And it's quite a beautiful thing to see. Now, hopefully, there's no planets around those systems, because it ain't pretty. It's still a violent process, even though I make it sound kind of gentle, how it's just slowly shedding these layers. But it's still very energetic. But that compares little to what we see on the right. On the right, we have what we call supernova remnants. When certain mass stars, typically high mass stars, die, they will explode. There's lots of different mechanisms to trigger said explosion, which we'll talk about toward the end of our course. But the point is, stars with a high mass will explode. And when they do, all of their material gets burst and shot out into space, and you get some remnant left over. And that's what we see in these 2 images here. Stars somewhere in the middle of those 2 regions exploded and sent all of the material outward in a very violent and energetic way. So that's what you see there. Okay. Now, we're getting into some very interesting things here. So we're talking about the deaths of stars now. So let's talk about the 3 main ways, well, 3 of the more interesting ways that stars die. First, a star like our sun will die in what you might think of as a boring way, but something very interesting remains. In this image, this is a real image of Sirius A, the big bright central star, and Sirius B. This is not a planet, this is actually a star, and they're both about the same distance away from us. So stars vary greatly in size and mass and luminosity and so on. Here we see a main sequence star, kind of like our sun. It's just bigger and brighter. But here we also see a star, but it's so much less luminous and tinier than the other. It's dwarfed by it. And I use that term for a reason. This is what we call a white dwarf star. A star like our sun will, when it dies, shed its outer layers so much, and it'll just keep doing that and keep doing that, shedding its layers. All that will be left is the core of the star. This is the core of a star like our sun left over. We call those objects white dwarfs for good reasons. They're white and they are small. Now, that's it. Our star is not going to explode, so it's not super interesting in that fashion. But white dwarfs are some of the most exotic objects in the universe. For reference, a white dwarf star is on average about the size of the Earth. This is not a real image, thank goodness. If we had a star that close to the Earth, we'd have some significant problems. But that just shows you the comparison in size. White dwarfs vary very little in size. They will either be just a bit smaller or just a bit bigger than the Earth on average. Now, because of that, something very interesting happens. These stars are still incredibly massive. The outer layers of the star that get shed, that's the low mass region of the star. The core is very dense. So we have a very massive and very small object. So it is incredibly dense. For reference, this is a great talking point in astronomy. If you were to hypothetically go to a white dwarf with a teaspoon, like a kitchen teaspoon, and you were to scoop up some of the material from the white dwarf and bring it back to Earth, hypothetically, of course, that material in that teaspoon would weigh 15 tons, or about 8 cars on average. A teaspoon, a kitchen teaspoon of this material, would weigh 15 tons. That is how dense this material is. It's unimaginable. But, that said, even though that's fascinating, it pales in comparison to some of the other more exotic objects in the universe. If a star is a bit more massive than our sun, it will die in a more exciting way by a supernova, and it will leave behind another core, another type of core. In this case, we call it a neutron star. So what a neutron star is sort of, I guess, in a sense, similar to a white dwarf in the way that they are formed, but a neutron star is even smaller, way more dense, and you get something very fascinating come out of this. So this is not a real image, again, of what a neutron star might look like compared to a city. So a white dwarf is exotic and it's the size of the Earth, but a neutron star is hardly any bigger than a city. Here we see it compared to the city of Vancouver. And also, too, what's fascinating about these objects is they're so small that they don't have much of internal heat, so they actually have a crusty surface, kind of like a planet would. But anyway, we'll talk about that more at the end of our course. But if these are even smaller, well, how dense are these guys? Well, do the same thing, take a kitchen teaspoon, and hypothetically go and scoop up some of that material. It would weigh 10 million tons, or about 2,500 cars. So again, insane. I mean, absolutely insane. And I don't remember the exact number, but this can be calculated. If you were hypothetically able to stand on a neutron star, which you couldn't, you'd be crushed under your own weight instantly if you even got close. But let's just say somehow you were able to stand on a neutron star. And say you hold out a penny at the height of your body. You drop it, say, 1 meter, and I don't remember the exact number, but you can look this up, it's pretty close. By the time it reaches the surface, just from dropping it a meter off the ground, it's traveling at, I think it's like half the speed of light, something like that. The point is, it's an incredible speed, because this object is so dense that its gravitational pull is so immense. But there is, of course, one more object that goes beyond anything else. If a star is very massive and it dies, when it explodes, it won't leave behind a neutron star, it'll leave behind a black hole. An object far more dense than a neutron star. It's so dense, in fact, that gravity is so strong that not even light can escape it. And you get a black hole. So this is actually an artist representation of a black hole, and in fact, I believe this one's actually from the movie Interstellar. Now, that black hole simulation in the movie is actually, from what I understand, the best simulation of a black hole that we have. So they did the research for that. So what you see is the black hole somewhere in the center here, and then material falling into the black hole. But that's the point. So black holes are probably the most fascinating objects in the universe. They're so dense that light can't even escape them. But we'll leave it at that for now. Okay, so we've talked about some smaller objects, just stars and stuff like that on their own. But let's expand a little bit. Let's talk about the grand scale of the universe. It's incredible how massive it can be. So here's a good question. Where do we live? So this is an artist representation of, I believe, the Milky Way. So we roughly live about there in one of the outer armbands of the Milky Way galaxy, which is a spiral galaxy given by its shape. And it's a barred spiral galaxy because you get a bar here. But anyway, we live roughly in one of these outer armbands. Another question is, how far out have we observed stars and planets? We've been surveying and scanning the heavens for so long now, relatively speaking, on a human time scale. But we've been looking out to the skies for so long, and we've been studying the stars and everything. So a good question, I guess you could ask is, well, how far out have we observed, right? We must have seen far if we've been doing it for so long, right? Well, inside of that circle is everything we've seen so far in terms of the stars and planets that we've analyzed. So even though we know of so many stars and planets, we've only barely scratched the surface of even our own galaxy. But we know there's tons and tons of galaxies out there and so on and so forth. So we've done nothing, effectively. On our time scale, we've done incredible things, but we have so much more to go. So this begs the question then, if we've seen that much stuff in such a small area, how many stars are there? In our own galaxy, at least, how many stars might there be? Well, current estimates have count at about 100 plus billion stars in our own galaxy alone. And as we develop newer and newer technology, we are able to resolve more stars and see fainter stars or further away stars. So right now, I think actually the current estimate might have been increased a bit to 200 to 300 billion. But the point is 100 to hundreds of billions of stars in our galaxy alone, which is incredible. That's a number we would never even want to count to. But that's just one galaxy. So wait a second. How many galaxies are there in the universe? If there's 100 billion stars in our own galaxy, how many galaxies are there? Well, this is an image, I believe this is the Hubble Ultra Deep Field. Almost every single speck of light you see in this image is a galaxy, not a star. I believe the only stars are these pointed ones here. So you get a star here, here, and maybe two up here. But everything else is a galaxy, each with billions of stars. So how many galaxies are there in the universe? Well, the current estimate places it anywhere between 100 billion and 10 trillion galaxies in the universe. So let's just say a trillion galaxies. If there's a trillion galaxies and each has 100 billion stars, multiply those two numbers together, and you're going to get a rough estimate on how many stars there are in the universe. That number? 1 septillion. That's a big number. Good luck counting to that. It wouldn't be possible in a human lifetime, or probably any lifetime. But the point is, there are an unimaginable number of stars in the universe. Now, we can make a good comparison. Since that's such a big number, we don't have anything to compare that to, right? Well, we can bring this down to Earth a little bit. Let's say you go to the beach and you pick up a handful of sand. There is an uncountable number of grains of sand in your hand, right? You wouldn't want to sit there and count every single grain of sand that's in your hand. That would just be ridiculous. But now, say you count every grain of sand on the beach that you're on. You probably couldn't do that in a lifetime, right? Well, to compare how many stars there are in the universe to grains of sand, well, you would have to count every single grain of sand on every single beach in the entire world. That's roughly how many stars there are in the observable universe. There are as many stars in the universe as there are grains of sand on all of the world's beaches. So that puts things into a bit of an earthly perspective for you. The last image I wanted to show, just in my little image series here before we get into some lecture material, is this here on the left. Now, what you're seeing is something very interesting. We might talk about this toward the end of our course, but we'll see how we get through our material. So you see lots of different galaxies here. These are elliptical galaxies. They don't have that spiral structure like this one here, like our own Milky Way, but they are still galaxies. But you'll notice that there are some weird lines or curves here. There's one here, there's some down here, some over here, and there's even some up here in the top right area. Those are not physically there. What you're seeing here, that is not something that's physically there. It's not a real image of what's there. I mean, this is an actual photo that we took. But this object that you see here is not real. It's not actually there. Same with all of these other lines that you see. What those actually are galaxies, but they are not there. What you're seeing is an image that was bent. The actual galaxy that is imaged in these lines is sitting behind this big cluster of galaxies. So this image here is not real. It's actually somewhere in the middle here. This is what we call gravitational lensing. A galaxy that is behind these clusters here is having its light bent around the giant mass. So you have a galaxy sitting behind these guys, its light gets bent around and placed over here. Now this sounds crazy, but this is real. Out in space, we have something that we call space-time, or the fabric of space-time. There's no physical fabric out there, but it's just this imaginary field out there. And when you have something heavy, it warps that space-time. So think, a great analogy is to think of, say, a bed sheet. Say you put a bowling ball on a bed sheet, maybe on your bed. The bowling ball warps your bed a little bit, right? It creates like a little divot or a little well, let's call it a well, where the bowling ball is. That's exactly what massive objects in the universe do to space-time. So here is an image, a schematic showing you what's happening. In the center, you have a large cluster of galaxies, just like we have here on the left. They're so massive that they're warping space-time, right? Imagine this being a bowling ball on your bed. It warps your bed just like the galaxy warps space-time. Well, as a result, the galaxy that's behind the cluster of galaxies, the light doesn't pass straight through it. The light gets bent along this curved space-time and gets to us. So what we see here on Earth is an image way off to the side, here on the left and on the right. We don't see a direct image of that galaxy in the background. So that is what's happening over here in this image. Just in another incredible thing that's going on in the universe. And one more bonus image. Here's a real image. It makes me laugh, sorry. A real image of gravitational lensing. It is a cosmic smiley face. So it's probably my favorite image in all of astronomy, just because it's so ridiculous. All right, let us continue. So let's just real quick kind of review or give a general statement on the scale of the universe. If you didn't know this already, we do live on Earth, and there's roughly 7.5 billion people on the Earth. The Earth is part of our solar system, which consists of the Sun, 8 planets, Pluto's not a planet, so there's 8, sorry Pluto, and all of the rocky material around it, so asteroids, comets, and trans-Neptunian objects. Our solar system belongs to the Milky Way galaxy, which has at least 100 billion star systems in it. Our galaxy belongs to a cluster of galaxies called the local group, which consists of about 70 or so galaxies nearby. The local group happens to be tightly packed in with a larger cluster of galaxy clusters called the local supercluster. Together, all of those superclusters that are out there make up the universe with roughly a septillion or 10 septillion stars. And here, okay, so real quick, I have an interactive scale of the universe. I didn't make it, so what I'm going to do is, if you're in my class, it will be posted on Blackboard for you to interact with. If you're not in my class and you're just watching these videos for fun or maybe for another course, welcome. And also, I will link in the description of my YouTube videos any resources that I put into my lectures. So if you look in the description, you'll be able to find a link to any videos or interactive things that I have as a great reference for you. So find that in the description. Now, here's a video that I would typically play, but because I'm posting these publicly now, I would like to avoid any copyright issues. So I used to play the videos in my PowerPoints, but again, I will just link them in the description for you, and I really recommend watching them when I have them here. So right now, I would go to the description and watch this video, because it's a great video showing you the scale of the universe. Okay, one last thing before we get into our lecture material. We're talking about scale, right? How big the universe is. I mean, a septillion stars, that's crazy. Well, one more thing. This is pretty recent, so I just thought I'd throw this in. We're not going to talk about nuclear weapons for more than a minute here, but this is the Tsar bomb, the most powerful nuclear bomb ever created on Earth. This is the most powerful detonation that we know of that we've ever made. It is equivalent to 50 megatons of TNT. In other words, that's 50 million tons of TNT. So, unimaginable destruction just from this explosion. But that's nothing. Here we have an image of MS0735. It is an active galactic nucleus eruption. Now, what is that? Well, we'll talk about that in a moment. But this is an image of the most powerful eruption that's ever been observed in the entire universe. You thought the Tsar bomb was crazy? That with its 50 megatons of TNT? Well, this is equal to 2 times 10 raised to the 39 megatons of TNT. So that's 2 followed by 39 zeros. And that's still megatons. So that's 2 times 10 to the 39 million tons. So, it's a little powerful, but that's a number we can't even comprehend. So let's try to bring it down in scale a little bit. Well, that eruption is equal to that many Tsar bombs going off at the exact same time at the same place. Still a number that I can't even say. I don't know what it is. It's just a huge number. So if you were to detonate that many Tsar bombs at the same time in the same location, you'd get something comparable to this eruption. Still too big of a number? Let's bring it down a bit more. If you were to convert the Earth's mass into TNT, so let's just pretend the Earth suddenly becomes a giant pile of TNT, you would still need that many Earths of TNT to detonate at the same time and place to give you that eruption. So, still a little bit ridiculous. Let's bring it down once more. Say you take the entire mass of our galaxy, okay, so every single star, every single planet, all the dust and gas that's in there, you take it all and turn that mass into TNT, then detonate it all at once in the same place, you would still need 10 million of those galaxies to detonate at the same time to give you this eruption. So, it's a little powerful. So thank goodness that hasn't happened anywhere near us, and hopefully it never does anytime soon. So real quick, what is an active galactic nucleus eruption? We will talk about this when we get to black holes at the very end of our lectures, but real quick, I'll give you a general idea. These are caused by the eruption of a supermassive black hole, just some of the most massive objects in the universe. They have a mass of over 10 billion suns. So this is an artist representation of one here, with material accreting or falling down into the black hole. These things are so energetic. I can't explain to you how energetic they are right now, but just you have all this material flying down onto this black hole with a mass of 10 billion suns. What happens is it gives off energy, and it gives off energy in 2 jets. So here's an artist representation of that jet. Material is flying outward at nearly the speed of light away from the black hole, and there's another one on the opposite side. Well, this is what, in a basic sense, an active galactic nucleus eruption is. It is the energy being released by a supermassive black hole. So in the image here on the right is you actually see an entire galaxy with these jets blasting through the galaxy. So this eruption literally punched holes through an entire galaxy with those jets. And you can see that, right? The jets are in the pink, and they punched holes, these cavities here, in the galaxy. So this eruption basically destroyed a whole galaxy. So good thing it wasn't near us. Okay, so we talked about the scale of the universe. Let's really quick just go over the history of the universe. All science right now leads us to the understanding that the universe began with the Big Bang roughly 14 billion years ago, and ever since it has been expanding. Much like if you blow into a balloon, the balloon expands. It's the same kind of idea. Within several 100,000 years after the Big Bang, neutral hydrogen had formed. So, in the early stages of the universe, before stars and anything like that, all that existed was hydrogen, helium, and a little bit of lithium. Within several billion years, matter had clumped into galaxies and galaxy clusters. Gravity eventually drove the collapse of those clouds of gas and dust to form stars and planets. So you get these big collections of gas and dust to form galaxies, and then at a more local sense, that material collapsed down to give us stars and planets. Stars then created heavier elements in their cores. So we mentioned earlier on that fusion is occurring in stars, so hydrogen fuses into helium in our own sun. But in more massive stars, you can fuse heavier and heavier elements. So this is where that idea from the famous Carl Sagan came from, where he says we are star stuff. We literally are, because before stars, there was only hydrogen, helium, and lithium. But we are made out of carbon, and our atmosphere is oxygen. There's iron in our blood. The only place that could have come from was the cores of stars. So these stars make these heavier elements, then they die, they either shed their layers or explode or both, and they enrich the galaxy and the universe with this new and heavier material. So, as I mentioned, got ahead of myself, they come together to form life, form planets and life like ourselves. So, it's a good point now to start kind of a brief lecture, just basic ideas here. Great question, what is astronomy? Well, I'll give you a technical definition, and then a definition that means more to me. First of all, astronomy is a term that is derived from Greek words. Their roots are astron, for star, and nomos, for arrangement or law. So astronomy literally translates to the arrangement of stars, or the law of the stars. Astronomy is the study of the origin and evolution of the universe, the physics and chemistry of celestial objects, and the calculation of their positions and motions. There's many branches to astronomy, which we'll break down in a second, but in general, these are the kind of things that astronomers do. But to me, it's more important to say that astronomy is about us. When we look out into the universe, we're looking into ourselves. Astronomy is a very humbling experience and field, and astronomy is just basically asking a couple questions in general. What are we? Where do we come from? And are we alone? I mean, these are the three biggest questions in all of our lives. And I don't think maybe the first two will never be answered. I don't know. I don't know if we'll ever know. But asking are we alone is going to be answered very soon. And I personally believe it'll be answered in our lifetimes. But the point is, these are the three big questions, and when we study astronomy, we're looking for these answers. It's a beautiful experience. We might not ever get to those answers, but the journey is incredible, and I hope to give you a taste of that through this course. So, I mentioned there are many branches of astronomy. I'm just going to quickly list them and what they do. We have astrometry, which is the precise measurement of the positions of stars and planets. So this could be some kind of orbital mechanics kind of idea, studying the orbits of planets, where they're going to be, where they are, this kind of thing. There's planetary sciences, which is the study of course, planets, but as well as asteroids and comets. So it's more local, studying the rocky bodies and the gas giants surrounding our star. There is stellar astronomy, which is what I specialized in my studies. This is the study of the origin, evolution, and deaths of stars. Each one of those three things is an entire lecture later on in our course. There is galactic astronomy, which I have not dabbled much in myself, but I did have graduate courses on galactic astronomy alone, and I have many textbooks on this alone. It is the study of the structure and components of a galaxy. Astrophysics. This is what my degree is in. It is the study of the universe and the physics of its components and constituents. So we're talking about analyzing the luminosity, temperature, composition, all these different physical quantities in terms of stars and other objects throughout the universe. So my degree is in astrophysics, but I focused on the physics of stars. So I mostly dabbled in stellar astronomy and astrophysics. We also have cosmology, not to be confused with cosmetology, very different fields. This is the study of the origin and evolution of the universe as a whole. So we treat the universe as a whole body and analyze what the universe is doing as a whole. And this is where physics really breaks down and gets weird. It's still very theoretical, but this is where people will branch out into string theory or the multiverse theory, where there's more than one universe, which I won't get into, but actually seems fairly probable. We then have a newer field called astrobiology. This is the study of the possibility of life elsewhere in the universe. This is a new and upcoming field. In fact, I studied at Florida Tech, and I think just in my last year, they started a new degree plan for astrobiology. So it's a very fascinating and exciting field today. And I'm sorry to those believers, but astrology is not a science. It's not real. I won't, ruin it for you too much, but there's no science behind astrology whatsoever. Not a single shred of evidence for it. It is not a science. So don't confuse astrology with astronomy. Something that a lot of people do if they're not experienced in the sciences. Okay, speaking of science, well, the foundation of all science is the scientific method. You don't have science without the scientific method. So, real quick, I'm sure you've learned this in middle or high school or whatever, but it's important to review because we need to know how important this is. You cannot be a scientist without making observations, using logic, and being skeptical at all times, no matter what. So the scientific method is a step-by-step process that everything has to go through. It's a rigorous field, and you need to be able to apply this to any work that you do. So typically, with any kind of scientific study, you begin by making an observation. So, you go look out into nature and say, what do I see? Doesn't matter what causes it or anything yet. You're just looking and saying, I see this. Then you can think of interesting questions, such as, why does this occur? Why am I seeing this? Once you think of that question, you can start to come up with a hypothesis or, your own idea or explanation for what you are seeing. So, okay, something weird's happening that I see. Why is that happening? Well, this is my idea. So that is your hypothesis. Once you've made a hypothesis, you can test it, right? You have to be able to test your hypotheses. So figure out a way that you can test this. And that brings you to the next step, which is to gather data and make your predictions. And test your predictions. So you figure out a way to test it, so go ahead and do that now. Once you've done that, you either can come up with a general theory as to explain what happened, or if your data collection and testing didn't go well, you can refine and alter it, maybe you can expand it, or if it just flat out doesn't work, perhaps you can reject that hypothesis and move to another. So this process is the foundation of all science, whether it be astronomy, biology, chemistry, physics, it doesn't matter. You need the scientific method. And we are lacking in that in some places today. It's not as important as it should be to some people. And we have to be very careful that we go through this process. Okay, before we go into our actual lectures, we need to define a few things. Most of these are incredibly basic, and you probably know 95% of this. But still, it is very important to go over them quickly. First, a star. In the general sense, it is a large glowing ball of gas which generates heat and light via nuclear fusion in its core. A planet is an object that orbits a star, and it's large enough for its own gravity to make it round. If a object is not large enough, it won't necessarily become spherical. That's why many asteroids and things that you might see have really weird oblong shapes. It's because they are not massive enough to make it spherical. We'll talk about that more later. But it has also cleared out most of the objects from its orbital path. So if you recall, I showed you an image of a protoplanetary disk where planets were forming. You could see that those planets are sweeping out paths in that material. So that is another requirement for a planet. A moon, the moon, which is a satellite, is an object that orbits another planet. I will use those two terms interchangeably myself, but just know that the moon is our satellite, and typically when we're referring to what people would say moons of other planets, they're really satellites and they do have their own names as well. But you'll hear me use them interchangeably as well. An asteroid is a relatively small and rocky body that orbits a star. So in our solar system, we do have what we call the asteroid belt between Mars and Jupiter, which is just a region with tons and tons of rocky objects that are much smaller than planets. And then we have comets, which are relatively small but icy-rich objects that orbit a star as well. And in our solar system, we have comets that mostly lie in what we call the Oort cloud, which exists far beyond the furthest planet, and sometimes they bump into each other and knock a comet closer, such as, for example, the most common one, Halley's Comet, which comes by something like every 70 years. Okay. A star system is a star and all of the material that orbits it, which includes planets and all the rocky, icy materials. So our star system is the solar system. A galaxy is a gravitationally bound system of stars, gas, and dust. Our galaxy is the Milky Way. And then we have clusters of galaxies, which is a collection of galaxies bound together by gravity. Our cluster is appropriately named the local cluster or local group. And then clusters form larger clusters called superclusters. So these are just giant regions in space where there's many clusters of galaxies tightly packed together. We then have, of course, the universe as a whole, which is just the total sum of all matter and energy, all of it, everything. That's what we consider the universe. And then just to make a quick distinction, we have the observable universe, which is the part of the universe that we can see here from Earth. So you'll hear me say observable universe a few times, most likely, throughout the course. So that's just what we mean. Okay, we're almost done with the terms, I promise. I need to define just a few things about motion because the first two here, at least, are very commonly used interchangeably, and it's definitely wrong to use them to use both for the same meaning. So anyway, rotation is the spinning of an object on its axis. So this would be like a top. If you were to spin a top on a table, the top is spinning around its axis, so it is rotating. The Earth, for example, rotates on its axis once every 24 hours. So that is how we have our days. But that is often confused with revolution or orbit. The orbital motion of one object around another due to gravity is a revolution. So revolution you could think of perhaps, a great example is the moon around Earth. That the moon is revolving or orbiting the Earth. It is not rotating around the Earth. So just make sure that you can just make a distinction between these two things. Rotation and revolution, even though they sound pretty similar, are different. And then we have expansion. So the universe as a whole is expanding, like I mentioned, like a balloon inflating. It is expanding, and so the average distance between all objects in the universe is increasing over time. All right. Last thing here for these definitions, we have to define some distances. Now this is very important because on Earth, we might measure a distance in, say, feet or yards, here in the US at least. Typically we use meters worldwide. But that doesn't work very well when we get out into the big regions of space. Space is huge. So we can't just use meters to describe things, or we're going to be adding tons of zeros to the ends of our numbers. So we define new distances. So the first distance that we discuss is an astronomical unit. This is the average distance between the Earth and the Sun. So one astronomical unit is about 93 million miles, or 1.5 times 10 to the 8 kilometers. That is that's 150 million kilometers. Excuse me. So this is a great unit to use when we're talking about distances within our own solar system. So, for example, the Earth is 1 astronomical unit away from the Sun. Mercury and Venus are a little bit closer, so less than 1 AU, and then all other planets are further away, so several to tens of AU. But if we move outside of our solar system, even that won't cut it anymore. If we're talking about distances maybe from one star to the next in a galaxy, well, then we might want to use a light year. Now, just to be clear, a light year is not time, even though it has the word year in it. A light year is the distance that light travels in 1 year. So a light year is equal to, 9.5 trillion kilometers, or 63,000 astronomical units. But even still, that doesn't always cut it. We do define one more distance that's a little bit bigger, and that is a parsec. Now, the technical definition of a parsec is very wordy, and it involves terms that we haven't talked about yet. So you can ignore, I guess, the definition of it for now. Just know that 1 parsec, given by PC, is roughly 3 1/3 light years, so just over 3 light years. So we will use all of these throughout the course. So if you ever hear me say astronomical unit, light year, or parsec, now you have at least a general idea of what I'm talking about. But notice how big these numbers are. That is why we express numbers in science using what we call power of 10 notation, also called scientific notation. It allows us to quickly and more efficiently write numbers. So for example, if there's a septillion stars out there in the universe, I don't want to have to write this number out. I could just write 1 times 10 to the 24. So this is a simpler way to write numbers. So for example, if you have a hard drive that is, a terabyte, let's just say. Well, if we wanted to write that, instead of writing 1 followed by 12, zeros? We could just write 1 times 10 to the 12. It's a lot more simple. So I'm not going to go through every single one of these in the table. This is just here for a reference for you. So if you ever need to look at how to write one of these numbers, or how to say them, or anything like that, you can always come back and reference this table. But what's important is to know how to write these things. So on the next slide, we'll just take a look at how to convert. If you have a number greater than 1, so for example, here I have Earth's diameter. It's 6.37 million meters. So if we have this number, how do we write that in scientific or powers of 10 notation? Well, you take the decimal place, which is technically at the end of the number here, and you move it to the left only until 1 digit remains to its left. So I'm going to move this to the left once, twice, 3 times, 4 times, 5 times, 6 times, until there's only 1 number to the left of my decimal place. So I move my decimal place to the left 6 times. The remaining number is then multiplied by 10, so you see that here, and raised to the exponent equal to the number of spaces moved. So I moved my decimal place in between the 6 and the 3, so it's right here. We then multiply it by 10 and raise it to the power of 6 because I moved 6 times. So that number is the same as that number. Now we do pretty much the same thing for numbers less than 1, just in the opposite way. This time we take our decimal place and move it to the right until you pass the first non-zero number. So I'm going to move once, twice, 3 times, 4 times, 5 times, 6 times to the right. So now our decimal place is between the 7 and the 5. We multiply by 10 again, but this time we raise it to a power, a negative power, because we moved in the opposite direction. So I moved 6 spaces to the right, so it's the -6 power. And this is the diameter of a red blood cell. So this very quickly is how you would convert a number to power of 10 notation. In this course specifically, we aren't going to do a lot of math. I tried to eliminate that a lot so we could just talk about the general ideas in astronomy. But whenever we do encounter some larger numbers, it is useful to write them in such a way. So keep that in mind. Okay, this is the last image of this lecture. I just wanted to leave you with this because it is fascinating. This is an actual image of Saturn. And I'm not just sharing this with you because it's a beautiful photo. It's a little pixelated because I blew it up to fit the whole screen. But you'll notice the arrow over here pointing to this dot. Do you know what that dot is? Well, that is the Earth. That's us. This is a real image of us. We're in this picture. You right now are in this photo. This is only taken, I think, within the last few years. So you are in this photo. So this is a picture of Earth from just beyond Saturn. In this class, I'll probably often give you a bit of an existential crisis. Because even though we are so incredible and humans are amazing creatures, despite all our imperfections, I mean, we're incredible people. And that said, despite how important we are here on Earth, I mean, look at this. I mean, this is every person that's ever lived right there on that speck. And that's just from Saturn. So, happy thoughts, right? The universe is huge, and that's a beautiful thing. So, I mentioned that there's videos, right? So I already showed one video earlier. At the end of this lecture, I like to show 5 more videos. So this is a video on the discovery of asteroids, just to show you how much stuff is actually out there around us. I then show you a video called The Most Astounding Fact. This is a very short, I think just 2 or 3 minute video of Neil deGrasse Tyson speaking. A beautiful video. I then show you a 2-minute video of, I believe it's Brian Cox on the right here, talking to Neil deGrasse Tyson about the universe possibly being a simulation. I then play one of my favorite videos. It's definitely not as serious as any of the others, as you can probably tell. It's called Why is the Milk Gone? I can't remember. There might be a bit of profanity a little bit, but it's more of a comedic view on all of this. But it does give you a heck of an existential crisis. And then to calm you back down, I finish with one of the most amazing videos of all time. It's Carl Sagan's Pale Blue Dot. So I will link all of these videos in the description. If you're in my class, I want you to watch these. If you're just watching publicly, I really do still recommend taking several minutes to watch these videos. It's a great complement to the course. And even if you don't even care for the course, you just want to learn more or be amazed, watch these videos. It's well worth your time. So this is the introduction. With the next lecture, we're going to start getting into the history of astronomy. So I find it important that the first thing we do is talk about how we got to where we are today in astronomy. So that's what you'll see next. So thanks for watching, and I'll see you there. Take care.